for yours.
Okay, so hello everyone. Thank you for being here for this week's algorithm learning in games seminar. This week we are very happy to have Clemens as our speaker. So Clemens is one of the seminar organizers and is an assistant professor at University of Waterloo. His research is on the interaction between economics and computer science, in particular on multi-agent reinforcement learning. So today he's going to share with us his recent work on stochastic approximation in multi-agent reinforcement learning. Without further delay, the floor is yours, Clemens.
Thank you for the introduction, Ife. Thanks everybody for coming. So basically what I plan to do today is give more like an introduction to one of the, I think, important methods in understanding multi-agent learning. So this is less my research, more kind of an overview of known results that are very useful, I think. And if we have time later on, we will talk a little bit about my research as well. So this method that I want to introduce, or that we heard a little bit about so far, is stochastic approximation. And basically it does this. So in general, you know, for many algorithmic learning schemes, you can think of them as stochastic difference equations. They live on discrete time every period to get some observations. And then you update your algorithm sequence. And of course, it's stochastic because usually you're learning in some kind of uncertain environment. Stochastic approximation is a method that, under some assumptions, takes these discrete stochastic systems and makes predictions about their behavior using a deterministic continuous time system. On the one side, it's often used to predict long-run behavior of the algorithms that's being done via a certain invariant set of the ODE once you've found the right ODE. And on the other side, you can also talk about finite time approximations via some tail probability bounds to think about likely trajectories of these algorithms and make uncertain predictions in finite time. A short history of the method. So this was introduced in the 1950s. Robinson Monroe, Kiefer Wolfowitz, and some others who introduced that method to study iterative optimization or route finding under noisy observations. And then over the decades, the method found used in engineering applications, signal processing, and so on, until it was also starting to be used by reinforcement learning researchers, evolutionary biology, and economic theorists like me today. Some important places to look at if you want to know, more the formal theory of this kind of method would be works by Benaim and Hirsch, and then books by Kushner, Nguyen, Borkar, and Marie Duflo, for example. I'll have like a set of references in the end if you want to take a screenshot of that. But this would kind of be a short history. So what I want to do is to introduce an example that we're going to use as a running example to study the method, which is stochastic fictitious play. We'll look at simulations of that, and we'll look at predictions that stochastic approximation can give us and see how these kind of, in what kind of sense we approximate these trajectories via an ODE. We'll also look at a short proof of that method, and then if we have time, we'll look at extensions of the method to actor-critic algorithms, multiple timescale schemes, and if there's even more time, we'll talk about my work on algorithmic collusion in repeated games. And of course, as usual, please interrupt me if there's any questions along the way. All right, so the example is a well-known example. So it was introduced by Fudenberg and Krebs in '93, stochastic fictitious play. In our case, we look at like a very simple version of that where there's only two agents. They play on finite strategy sets, AI, choosing pure strategies or mixed strategies, which are going to be called sigma on the set of distributions over AI. They will be endowed with payoff functions, Bernoulli payoff functions, and expected utility payoff functions that evaluate their expected payoffs based on mixed strategies of their opponents. These players are going to play repeatedly on discrete time increments where an action history is going to be bold-faced AN of these actions that have been taken of these agents over time. And the players are especially interested in keeping track of empirical frequencies. So an empirical frequency, which I call xin of A, is player i's frequency of choosing action A in the last n periods. And in general, for any mixed strategy, I'm going to call a best response function for player I as the set of argmaxes of their expected utility function given a mixed strategy sigma mod I. All right. So for anybody who's been around in our first talk, we talked about plain vanilla fictitious play, for every period players choose according to their best response based on their opponent's empirical frequency of play. Interpreting, if you want, the empirical frequency of play as a predictor of their opponent's next period behavior. In stochastic fictitious play, players are a bit more cautious in the sense that they now choose probabilistically, and they choose probabilities that are proportional to the expected payoff given the opponent's empirical frequency of play. So for some positive lambda, we have this softmax or logic response function here, where the larger lambda is, the closer you get back to BI, the best response function, the more weight you put on the argmax. And I'm going to call this function BI tilde of empirical frequency and lambda. So that's stochastic fictitious play. Every period you choose randomly based on this logic response function. What we're interested in is making predictions about the empirical frequency of play of all players. So I'm going to call AI n+1 the action of player I realized based on their logit softmax probability distribution. And then we can write xn as a difference equation for each player. Xi n+1 is xin plus the increment of your empirical frequency, where I call bi n+1 now the vector of the realized action. So it's going to be all zeros except for the one in the entry of the action that was actually chosen in that period. And that's how you can write, succinctly the empirical frequency evolution as a recursive stochastic difference equation. So how could this evolve? Let's look at some simulations. There are two 2x2 games here that I'm looking at. On the x-axis, I'm plotting player 1's frequency of choosing action 1. On the y-axis, player 2's frequency of choosing action 2. And I initialize these simulations at some points in the plane here. And then I run smooth stochastic fictitious play. On the left side here, we have a prisoner's dilemma where action number 2 is the dominant action. All of these simulations, as you can see, converge to the 0,0 point, which is the unique Nash equilibrium in that game. So that's kind of nice. On the other side, we have a Battle of the Sexes game, same initial points. And it has these two pure strategy Nash equilibria, which these guys all converge to, 0,0 and 1,1. So these are the simulations. That's the picture that the simulations give us. And now we can show how stochastic approximation tells us the story, the analytical story of what's actually going on here. All right, so let's look back at our stochastic difference equation for the empirical frequency. You can write these as well in this way, where tomorrow's frequency is today's frequency plus some step size times the expected update, which is just the expected value of your realized action, minus xin plus an error term. In our case, alpha n, the step size is just 1/n+1. And this error term is just the difference between actual realized action and the expected update. And now you can notice, so I just added and subtracted the expected update. And you can notice immediately that this error term is pretty well behaved. It has a conditional average of 0 and a conditional bounded variance because, these realized actions and the probabilities all live between 0 and 1. So the error term is very well behaved. It's a bounded variance martingale difference sequence. So that's our stochastic difference equation. And now stochastic approximation is going to tell us that we can take this difference equation and approximate its long-run behaviors via solutions to an ODE, which we can eyeball will be kind of the first terms here, not the error terms, because these are going to be averaged out. Whoops. So the ODE we want to look at, which I call perturbed best response dynamics, is just going to be b tilde of x minus x on the right-hand side, where b tilde is now the stacked b tilde I over individuals. And I suppress the lambda because I'm just going to keep it fixed from now on. And I'm also going to quickly call this f of x. Now, the first step in figuring out how this ODE is connected to the stochastic approximation scheme would be to bring the discrete time system onto continuous time. And the way to do this is by thinking of alpha n as the continuous time steps that the discrete time algorithm takes. And then in period n, the continuous time that has accrued after n algorithm steps would be just the sum of these step sizes. So we call tau n the continuous time that has accrued after n algorithm steps. So that's just the sum over these alphas. And then we can write the linear interpolation of our empirical frequencies as x bar of t, which is just an interpolation between xn and xn plus 1, as long as t is between these tau n and tau n plus 1 terms. And now here's the set. Go ahead. Yep.
So when you write this difference equation, you want to find, so the B tilde is the distribution that you have given, parameterized by lambda, and you want to solve it in the sense that you try to predict the dynamics of these xi's. Is that correct? I mean, that's just...
Yes, pretty much. So I'm going to look at specific invariant sets of this ODE, and those are supposed to be predictors of long-run behavior of the XINs.
And now you replace x by a continuous variable. I mean, xi and the x dot is now something that you try to get as a continuous function of time.
The x bar is now, yeah, exactly. It's me bringing the discrete time.
Yeah, it's just I understand correctly. I think I do, but thank you. I just wanted to double check. Thank you.
Yeah, yeah. All right. So here is the assumption that we're going to be making for our stochastic approximation scheme to work. So up here, I've just rewritten our algorithmic updating scheme overall, stacked over all individuals. And these are standard assumptions. They're sufficient. They're by no means necessary. There's a lot of weakenings of them, but this is kind of the very succinct and quick way of writing very nice assumptions here. The first one is on the step sizes. We want our step sizes not to be summable, but square summable. And the intuition here for the non-summability is basically that, we want to be able to connect the trajectories of the discrete time system to solution curves of the ODE, which can run over infinite time in the continuous time world. So we want the step sizes of the algorithm also to be able to map into the infinite continuous time. On the other side, we want to be able to average out these error terms, and that's why we need square summability. The next condition, f being Lipschitz continuous, basically gives us also the nicest predictions because in that case, the ODE has unique solution curves, can also be weakened, in which case still a lot of things go through. The next condition is on the niceness of these error terms. So we're saying there exists a sequence of sigma algebras, which you can think of as the information accrued by the algorithm over time. Such that given those sigma algebras, Mn is a square integrable martingale difference sequence. And finally, we're making this assumption on bounded iterates. And that's a pretty strong assumption in some cases. So we're assuming from the get-go, even though we want to make predictions about Xn, we're assuming that it's bounded almost surely. In some cases, you can verify this. In other cases, people just impose it or make all their predictions conditional on the event that the iterates stay bounded. But it might be pretty hard to verify the probability of that event actually happening. In our case, it's going to be immediately implied.
Quick question.
Yes.
It's immediately implied because it's in the simplex. This
Yeah, exactly.
Right.
There's another slide where I explained. Yeah.
Okay.
Yes. So here, this is just taking these assumptions to our example. This assumption immediately holds because our step size is just 1 over n by construction. Fx is Lipschitz. Our b tilde function is smooth in X, so no problem there. We need to find a sigma algebra for which this holds for our error terms. And in our case, remember that these error terms are just the difference between realized action and expected action. And in that case, if we take our sigma algebra to be the sigma algebra that is generated by the past history of empirical frequencies, that is more than enough for this result to hold, because players just play an action conditional on the current frequency. And finally, boundedness. By construction, the empirical frequency lives in the simplex, so everything is bounded. Not even almost surely, but surely. Okay. And here is now the sense in which our approximation by ODE solutions applies to the empirical frequency stochastic process. So take a solution of our ODE, which I call phi t of x. It is a solution that starts at x and takes it t periods forward in the continuous time. We define x bar t, so this is now any function, to be an asymptotic pseudo trajectory of this ODE. If, let's look at this difference on the inside here, we take an interval from 0 to capital T, and we look at x bar starting at some t, and we compare it to a solution that takes the same starting value x bar t and carries it as periods forward. So we look at the linear interpolation of our algorithm from t to t plus s, and we compare it to the solution curve that starts at the same point and goes as periods forward. And now we look at the supremum the uniform distance between this x bar t and the solution overall as between 0 and capital T. Once we take the initial period to infinity, we want this difference to go to 0 for any interval of 0 to capital T's. So this is a very strong, pseudo trajectory property if we can prove it holds for our empirical frequencies, because it really means not only are we talking about the limit point of x bar of our algorithm, we're actually talking about as t goes large, our x bar is supposed to shadow very closely solution curves of the ODE. And the result is truly that under our assumptions, almost surely will x bar t be an asymptotic pseudo trajectory to the ODE. So almost surely, very closely will you be shadowing solution curves of the ODE with your stochastic difference equation. From asymptotic pseudo trajectory, you might not be immediately able to see, what kind of behaviors does this now predict? Like, what kind of solution curves are we actually looking at when we're talking about taking the ODE and approximating and predicting long-run behavior? So we need to talk about long-run behavior of our time interpolated system and ask what kind of specific solutions will we actually be seeing when we look at the long-run behavior of the algorithm. So let's define L of x bar to be the set of convergent subsequences of an asymptotic pseudo trajectory x bar. So these are all the lim subs and lim imps of this x bar. Here on the right-hand side, what I'm defining is x bar taking from some starting value to infinity, take the closure of that set and intersect it over all S, so you get all the lim subs and lim imps. And here's the result by, I think, initially Benaim and Hirsch from 1996. If you take an asymptotic pseudo trajectory of an ODE, then the limit set of this pseudo trajectory is an internally chained transitive set of the ODE. We're going to define this in a second, but this is now a specific solution to the ODE. And on the other side, the partial converse is that if you take an ICT set of the ODE, and the domain of your algorithm is a locally path-connected domain, for example, in our case, this holds, or in the Euclidean space, this holds, then you can find an asymptotic pseudo trajectory that will find this internally chained transitive set. So there exists at least one. There could be only one, so it's still a very low probability of finding it, but we can talk about probabilities later on. So this is the connection. These are the specific sets. And let me define them now, because I haven't defined them yet. An internally chained transitive set is a specific invariant set of the ODE. So if phi of tx is a solution to an ODE, then a compact set of the domain of the ODE is invariant whenever phi t applied to that set is not going to change that set. It's not contracting it or expanding it or changing it in any way. This set is an attractor if it's not only invariant, but also there's a neighborhood around the set such that if you start in the neighborhood, you will converge to that set. And finally, with these two definitions, a set is internally chain transitive if it is both invariant and, if you look at the flow restricted to this set, this flow has no proper attractors, so it's not going to shrink into some subset of the invariant set. And what this means for us is the following. First of all, rest points and periodic orbits of the ODE, those are all ICT sets. So those would all be candidates for what the algorithms could learn if they're playing based on that ODE. But the thing is a bit larger than that as well. So if you have, for example, multiple periodic orbits that touch each other non-trivially on a longer kind of subset of the space, then the union of those two periodic orbits would also be an ICT set, because there's no proper attractor for that either. So you might get into trouble if you only think about, you know, singular specific orbits or something like that. All right. So here's what the picture looks like now after our intuition about stochastic approximation. What I'm plotting is the same initial values, the same simulations, but now what I'm overlaying here is the solution to the ODE starting at these initial values. And as you can see, the shadowing property really seems to apply here, right? All these solutions converge to this equilibrium down there in the prisoner's dilemma, and shadowing seems to be pretty nice. The same thing is true for the other game, the Battle of the Sexes game. All of these solution curves are sort of being shadowed by the trajectories of the stochastic process. So this really strong property can be actually pretty nicely verified here. All right, so let's look at a proof of this result. A couple of definitions first. I'm going to define bracket of t for continuous time t as the continuous time in the algorithm world that has accrued in order to achieve something that is as close as possible to continuous time t. And this is basically now a step function that changes only whenever the algorithm time step size also changes. And also I need to bring these martingale error terms onto the continuous time. So I'm going to call this m hat of t for any t in tau n to tau n plus 1. And now let's fix a capital T. So this is going to be the continuous time period on which we will compare the algorithm to solutions of the ODE. And we're going to take some small m such that our algorithm time tau n plus m is within tau n to tau n plus t, so that we look at something within this interval. Then you can write your algorithm at tau n plus m as the algorithm at tau n plus all the updates that have accrued between n and n plus m. So those would be just step size times update. And you can write this based on using our definitions, you can write this as an integral now. And that's nice because it's going to help us compare directly to solution curves of the ODE. So we get this integral representation, which I repeat here. And we compare this to a solution of the ODE starting at the same starting value x bar tau n, which I'm now going to just call phi of t. And that's just, you know, the usual definition. By construction of a solution, it must satisfy this equation. And what we want is compare these two guys. So we just take a difference and look at the norm of that. On the left-hand side, that's what we have. And on the right-hand side, this is now upper bounded by the integral of the norm of the ODE applied to the linear interpolation and the solution of the ODE, and the accrued error terms over time. What I want to do now is add and subtract this guy, which is f of the solution at these bracket t time increments, because that allows me to bring these two onto the same sort of time scale. And that adds one error term, which is very easily handled. So this error term now is an error term, the blue one, that only depends on the deterministic solution of the ODE. So this is only the difference that I introduce once I introduce this bracket t increments for phi instead of the continuous time on which it actually lives. And finally, we repeat our stochastic error term of these m hats. And we end up with these three error terms, which we can bound now. So the first bound would be on this deterministic error term. Since our ODE is Lipschitz, you can bound this by just the difference, the integral of the difference of these solutions between t and bracket t. And now remember that bracket t changes with the step size of the algorithm, and these step size are going to slowly dissipate to 0. So this difference for every t is upper bounded by some constant times the step size. And that means in the end, the whole difference of the integral here is upper bounded by the squared sum of these alphas, the squared tail sum of these alphas. And since the alphas are square summable, the tail sum converges to 0, so that the whole term here, even in supremum over the ending time, has to converge to 0 as the initial time n goes to infinity. Similarly, if we look at the second or the third error term, the stochastic error term, that's just this weighted average of these martingale difference terms. And because that's a square integrable martingale, we get a martingale convergence theorem that holds. So the tail sequence of these of this series also has to converge to 0. So we also get rid of the stochastic error term. Now that's nice because we can look back at our initial difference that we want to consider, which I've rewritten here. Again, applying the Lipschitz continuity of f, we get that the final summand here, the difference that we're interested in, is upper bounded by a weighted sum of the same terms. And that's why we needed this bracket t for phi and for x bar. So that we get these kind of on the same time scale. And once you have an expression like that, this is an application of the Gronwall lemma, which allows you to connect this kind of final summand is related to the previous weighted sum of these iterates. And what it gets you is kind of that the summand itself is upper bounded by this exponential term, which is constant because we look at a fixed capital T, multiplied by the rest of the summands on this bound here. And now we know that both of these are converging to 0 as n goes to infinity, and therefore also the left-hand side here goes to 0. And you know what I've shown you here is only on the discrete timescale for n and m. What we actually want is continuous t and s from the definition of pseudo trajectories, but that's pretty quickly done by realizing again that the step sizes go to 0. So these tau n's are really going to cover very soon all of the continuous n's as well. And that gets you the results. So that's how you get from your discrete time difference equation to a continuous solution. Okay, so this was just to give you a short kind of intro to how these errors kind of get introduced. That helped me to kind of visualize as well, if I want to make statements about the finite time, how do these relate to the exact errors of this process and so on. And that's what we get on the next slide here. So now that we know the long run result, here's a finite time result. In finite time, we can bound a tail probability, and specifically what all we're going to need is this inversion. So for any continuous time, I'm going to write m of t as the algorithm time, discrete time that has to accrue in order for the algorithm continuous time to pretty much reach t. And in that case, so once we have that defined, we can make the following statement. There's a function from t and alpha such that for all capital T and all delta, we get that the probability that our algorithm x bar is delta shadowing this ODE solution, conditional on the initial information of the algorithm at MT, is upper bounded by a Chebyshev inequality with CT in the numerator. And CT has this nice property that it converges to 0 as alpha converges to 0. So the smaller the step size, initially, when you're looking at this inequality, the closer in probability can you predict your algorithm frequency or your algorithm actually to track an ODE solution. This result also holds for step size sequences that don't converge to 0. What's enough here is that, again, look at any fixed alpha. The algorithm runs on some fixed alpha. The smaller this alpha is, the larger the probability that it will be tracking a specific solution to the ODE. Okay. If there are no questions, then yes. So here is a visualization of this result, basically. So what I'm doing here is I'm fixing the initial condition. It's always going to be 0.4 or 0.1. And looking at our stochastic fictitious play algorithm at different starting times. So as it learns more and more stuff, if you want. When we initialize at the very beginning, you can see that this process is kind of wacky. A lot of it still converges down here to the equilibrium, but it also goes all over the place. As our initial time increases, the shadowing property becomes more and more visible. And that's kind of the idea of these plots. With larger and larger initial time, nicer and nicer shadowing of the ODE solution will happen. That's kind of the intuition I want to get across here. Okay. Now, what about selection? There could be many internally chain transitive sets of the ODE. Are all of them going to be potentially learned by the algorithm with positive probability? Or could we say that some of these ICT sets are actually never going to be learned by the algorithms? So once we've defined the set of, the invariant sets that can be learned by the algorithms, we're still not done, because we have this stochastic process that might actually never reach, with probability zero, reach only some of these potential outcomes. So here's one result about attractors, which is unsurprising. One definition that we need is that attainability, so a given set on the domain of the algorithm is attainable if for any neighborhood of that set, there is some period in the future such that the algorithm will hit that neighborhood with positive probability. And this property is, for example, satisfied by our linear interpolation in the stochastic fictitious play world for the whole domain, for the whole simplex. But it's something that is required to check if you want to get to the next result. So the next result is then that under our assumption on the stochastic approximation assumption, if you have an attractor of the ODE, which is an ICT set, as we know, then if the set of attainable points of your process intersects the Bazin of attraction of the ODE, of the attractor, then we can conclude that with positive probability, the limit of the asymptotic pseudo-trajectory will find this attractor. So attractors, under attainability, attractors will be learned with positive probability. There is a partial converse to that. It requires one more assumption, though. So suppose that there is a rest point of the ODE that is not an attractor. It's an ICT set because all rest points are ICT, but it's not an attractor. It's a very nice, linearly unstable rest point. That means that at least it has one direction in the space under which the ODE repels from that rest point. The next assumption basically says that whenever the algorithm is close to this rest point, the errors that it makes, the martingale difference errors conditional on the time that you're there, are going to have positive variance in all directions. So the algorithm could explore any direction in that neighborhood. Under that assumption, it might not be so surprising to think that, that this implies that whenever the algorithm gets close to that rest point, it will hit the repelling direction of the rest point infinitely often. And when it does that, it's going to be impossible to reach the rest point. And here's the result then. Under our stochastic approximation assumption and this additional assumption on the variance, the probability that you will find this ICT set is actually 0. So we know that, for any ICT set, there exists a pseudo-trajectory that will find it, but this just says that the measure of these pseudo-trajectories is going to be very small. And this gives us a very nice selection result because it tells us that, for example, if you can guarantee that all your ICT sets for the game that you're looking at are rest points, for example, Nash equilibria, then this means that not all of these Nash equilibria may be learned by the algorithm. Even though they're all Nash equilibria, you can already tell that those that are unstable will not be learned by the algorithm. And you can talk about actually non-trivial selection of your multi-agent learning process. All right, so what time is it? Oh, very good. So if there are no questions right now, we can talk about extensions to the method. And maybe one thing I wanted to mention is if we look back here on the right-hand side, you might know that the Battle of the Sexes game actually has 3 equilibria, one of them being mixed. It's somewhere here in the middle. I didn't have time to plot all of this stuff. But what happens here is the application of selection to our problem. When you initialize this algorithm globally, it's never going to learn what is the perturbation of the mixed strategy Nash equilibrium in this world where we're playing perturbed best response dynamics with the softmax choice probabilities. Only these two equilibria are attractors. The middle equilibrium is unstable, and the algorithm is never going to learn it, or with probability 0 at least. All right. Okay, now back to extensions. So I think an interesting extension to this stuff is actor-critic algorithms, because they show up a lot in modern reinforcement learning. So these are algorithms that involve two updating schemes instead of one, which we've seen so far. And usually also what the name suggests is that, one updating scheme is about updating a policy function, and the other updating scheme is an estimate of performance, for example, some kind of value function or the gradient of a value function or something like that. And one reason to introduce this separation of policy update and critic update is a reduction in variance of the policy updating scheme. So you can think of, if your value function updates are noisy, because of course you're making these estimates when you're computing your value function, and you just use your policy immediately on that value function, you're also tracking exactly the noise that is generated by the value function update process. But if you dampen the updates of the policy a little bit by introducing this kind of update for policy separately, you're also dampening the noise that is introduced from the value function updates. And this is kind of one idea of introducing actor-critic. There's also more possibilities now for us, because we have two separate updating schemes. We can look at two separate step sizes for these schemes, and that introduces these two timescale approaches, which can be very useful in a lot of places, and we're going to look at one of these now. So what I will do is basically just turn stochastic fictitious play into an actor-critic algorithm. And to make it a bit more interesting, it's not going to be exactly stochastic fictitious play, but more like XP3, where a player doesn't actually know their payoff function, but makes estimates of the payoffs. So what I'm introducing is these weights, WIN of A, which is player I's estimate of action of the payoff to action A in period N. And then these players are going to think about these softmax weights now in terms of these expected payoff estimates. So BI of WIN for some fixed lambda positive is going to be just a softmax function as before, but now we're using these estimates instead of the actual payoffs conditional on the empirical frequency of actions. And players will draw actions from some mixed strategy distribution, which I will show you in a second. But at each period, they draw actions from there, but they only observe their own actions and their payoff realizations, not their actual payoff function. So if AN is the realized action in period N, they're going to look at these estimates for their payoff in period N of action A. And this should remind you of XP3 if you know about the algorithm. This is an estimate that takes the indicator function. If you took action A, give me the realized action of the realized payoff of that action and divide it by the probability with which I would have chosen action A. Why do we do this? Because this construction actually gives us that we get an unbiased estimator for the expected payoff to action A, conditional on our current strategy profile. So when you take expectations here conditional on the strategy profile, this guy drops out and you get something that tells you the expected payoff exactly to action A, conditional on your opponents. And this is exactly what the stochastic fictitious player wants to have. So if we can figure this out, we will get back to a stochastic fictitious play. So I'm going to form the critic updates then as these weighted averages. So tomorrow's critic value is today's critic value plus some step size times these estimates VIN minus the current weight. And this is basically, the recursive form for a weighted average over these VINs for some weight alpha n. And now doing the usual thing, which we did for stochastic fictitious play, we can plug in the conditional expected value from the update and add an error term, which is again very well behaved in our case. Bounded variance stochastic, bounded variance martingale difference noise. For the actor, we'll introduce this cautious update. Tomorrow's mixed strategy is today's mixed strategy in a convex combination plus this BI softmax term given the current weights. So instead of jumping directly to tomorrow's softmax of tomorrow's weights, we're going to be cautious in our update and form this convex combination for some sequence Bn, beta n. Now, writing these two schemes together is now exactly the representation of an actor-critic algorithm. And then we can apply stochastic approximation to this coupled system. One more thing we can do now that we have these potentially different step sizes is introduce a 2 timescale approach to this. So that's what I want to do. One thing you can do is, for example, bring these step sizes onto different orders of magnitude such that beta n over alpha n converges to 0 with n. And that just means that the actor's update lives on a much slower timescale than the critic's update. The critic is much faster, which you can also think of as asymptotically. Out of the view of the critic, the actor is pretty much constant. Policies are constant. The environment of the critic is stationary, and that, is a very nice place to form your expected payoff estimates, which we will see is also directly implied from stochastic approximation. So if we again look at our system and merge the timescales into the timescale of the critic, so we get this alpha n for the critic, which is always there. Here we multiply and divide by alpha n. Then the right-hand side of this ODE here is 0 in the limit, because the right-hand side here is bounded and this converges to 0. So the associate ODE to this timescale is going to be the interesting one where sigma.I is 0 and w.I is this linear system. On the left-hand side, we have a constant sigma I with a globally attracting unique rest point, which is just the expected payoff given the fixed sigma that you started with. So the critic, as you might expect, is in the long run going to converge to the correct expected payoff for the correct sigma, even though sigma actually moves over time. So going back to the algorithm time, infinite n, because of the result of the critic, we know that the weights are going to get closer and closer to the correct expected payoff estimate. So if we go back to actor time, which lives on beta n actually, right? Which is the slower of the 2 timescales, we can rewrite the actor's update by adding and subtracting the correct softmax for the correct expected payoffs. And this is now the softmax of the stochastic fictitious player. And we're adding and subtracting this so that we get a new error term, which is just the BI of the weight, of the actual weight, and BI of the expected true weight. And we know that this one converges to 0 in the limit in probability as alpha n converges to 0. So all we're doing here is we're introducing a new error term, and this error term is going to average out just like the martingale difference error that we had before in our stochastic approximation proof. And that means that just applying stochastic approximation again, we end up with the associated ODE for the actor as exactly the one that we had for stochastic fictitious play, only that now we're looking at policy profiles and not empirical action frequencies. And we get exactly the same picture again, only a little bit more noisy, so I didn't generate the simulations there, but the prediction is exactly the same. And that's, kind of the beauty of this approach. It applies also in the stochastic sense, and it gets you some very nice results if you introduce these 2 timescale kind of methods. Any questions so far? I don't know if I was going a bit too fast here, so please, if something was kind of unclear, always let me know. All right. So yeah, so this is 2 timescales for an actor-critic learner. Now, since if there are no questions and we have about 15 minutes left, we can talk about my work in this area, or at least one of my recent works in this area. And that is thinking about actor-critic learning to play repeated game strategies. What I was interested in here basically was this question of algorithmic collusion, which came up while I was doing my PhD more and more in economics. And I wanted to make theoretical predictions under which conditions you can expect algorithms to learn collusion when they can play repeated game strategies. So an example that does this from my paper is look at a simple game where there's 2 agents and they choose quantities on an interval. So these are Cournot competition agents. They choose quantities on some interval. We look at the aggregate quantity capital X. And prices for these agents are realized randomly, conditional on the aggregate supply on the market. The larger the aggregate supply, the smaller the expected price. Payoffs then are just, or expected payoffs then are just the price times quantity minus cost. And we're going to think about payoff functions that are very well behaved. So we're going to call regular payoff functions those payoff functions under which this stage game has a unique Nash equilibrium that is interior and is therefore also globally attracting for players that only play stage game strategies. But we don't care about stage game learning here. We want to know about repeated games. So the kind of repeated game that I want to look at is one in which players do imperfect monitoring. So we have, I'm introducing the state variable, which is commonly observed by the agents, and that's their monitoring tool. Basically, they can't see each other's actions of the past, but they can see a random variable that is correlated to past actions. And that way you can do inference about your opponent's actions and punish them if you think it's likely that they made a deviation from the equilibrium action that you were supposed to play, for example. As an example here, prices are correlated to actions. So one simple state variable would just be asking, was last period's price low or high? In general, though, we're going to think of these states as a controlled Markov chain. Any correlation structure is allowed as long as it's an irreducible Markov chain, as long as the states are an irreducible Markov chain for any choice of quantities. Okay, rational players in this game have the objective of maximizing expected future discounted profits. And we are constraining them to choose only policies that are Markov policies conditional on the state variable. So they're all observing the state variable, and we're asking them play only policies using this state variable. And in that case, we can define a Markov perfect Nash equilibrium using these kind of policies in the usual way. Every player is best responding to each other. And notice that, Markov perfect Nash equilibria are Nash equilibria of the whole repeated game, allowing for any history-dependent strategy. As long as your opponents are playing Markov strategies, there is a best response for you to also play a Markov strategy. So this is a general Nash equilibrium of the repeated game. All right, so now instead of agents that are rational, we're going to have reinforcement learners playing this game. And we know now what actor-critic learners are. We know what 2 timescale approaches are, so I'm not going to talk too long about this. But basically, think of actor-critic learners playing this game. They have an actor scheme that updates their rho TI functions, which are their policies, over time. And they're going to have a value function estimator, which are called QTI, which is, if you know, Q learning is a Q action value function. And they're going to have this estimator running at the same time. So it's an actor-critic scheme with the goal to update policies towards best responses of your against your opponent's policy. Shortly here, the policy updating rule would be a convex combination of today's policy and the estimated best response based on your QT state action function, plus some noise term that I introduced to support exploration. which is one way of dealing with learning in continuous action spaces, which we haven't really talked about. The Q estimator, this QTS of X function, is an estimate of Q star, the true state action value function, and this is basically the inside of your Bellman iteration Bellman operator. It's a function that you can use to read off best responses from. So the connection is basically the maximum over X for every state is equal to the true value function of the player. And yeah, I'm just going a bit quicker because I want to get to the interesting result, but I hope everybody is on board with Q learning, or at least with these Q functions. So basically the interest is, if you're able to estimate your Q function, your Q star function, knowing your Q star function is sufficient to find a Markov best response to an opponent who always plays row T, not I. So this is a sufficient statistic for that. All right, then now, we want to apply stochastic approximation again. So the ODE that we can connect to is going to be related to best response dynamics. Basically, what I define as the state-dependent best response dynamic is a best response dynamic that lives in the policy space, not in the stage gain action space, where I define this ODE here, BR bar of S being the stacked best response function given a state variable stacked over individuals again. And BRS for each agent is just the optimal policy among Markov policies if the objective is expected future discounted profits. So this is basically plain vanilla best response dynamics, only that now players think about Markov policies instead of stage game actions, and the objective is expected future discounted profits. And that's exactly the ODE that approximates the behavior of our system of these agents that try to learn repeated game strategies. And here's the result. So now we already looked at selection, so I jumped directly into the result. If you have an equilibrium, or yeah, what I forgot to define here, I just grabbed these slides really quickly. What I forgot to define is E of S is the set of Markov perfect Nash equilibria of the repeated game if policies conditional on the fixed state variable S are used. And the result is then, if this equilibrium is attracting under our ODE state-dependent best response dynamics, then the algorithms will learn it with positive probability. Rho infinity here is the limit set of our algorithms. On the other side, if it is unstable, we can actually make a stronger statement. There's a whole neighborhood around this equilibrium if it is unstable, such that the algorithms will hit this neighborhood with probability 0. So again, you get this kind of selection prediction. If you want to know what the algorithm is going to learn, if you can't, for example, promise that it will converge to an equilibrium, then you know that it will avoid equilibria that are not attracting under the ODE. And I'm going to skip this really quickly because I want to get to the punchline, or at least this is a partial punchline. What I wanted to know in my paper is more of a regulatory question then. It is, if we know that algorithms may learn to collude with each other when they play repeated game strategies, how can we potentially regulate this under, what is important for these algorithms to learn collusion versus maybe not collusion? And what I think of as not collusion here would be if these algorithms learn to just repeat the stage game Nash equilibrium in every state. So remember that, under regular payoff functions here, there is a unique Nash equilibrium to the stage game. I'm going to call this Q of n, a fixed quantity. And now let a policy profile be such that in every state, Q of n is played. That's always a Markov perfect equilibrium for any possible state variable. So it's a candidate ICT set for our ODE. It's a candidate outcome for the learning process. But it's only going to be an outcome with positive probability if it is also attracting. And what I was interested in then is asking, under what kind of state variables is this most competitive outcome attracting? And it's true actually that it is not always attracting. The state variables are really essential here. So basically, whatever somebody who writes down the algorithm thinks of as an important state variable, an important kind of information set to condition on, is really essential in whether these algorithms can learn to collude or not. And the result here is saying exactly that. If we take a regular payoff function and you take this rho star, which is the repetition of the static Nash equilibrium, it is attracting and therefore learned with positive probability if and only if this bounding condition here holds. And what's important is that this eta function depends only on the absolute values and derivatives of this transition probability of the state variable. So this is a quantity that only depends on details of the state variable and the distribution of the state variable. And these cutoff points depend only on details of the payoff function, which has nothing to do with the state variable. So that means that once you have the cutoff points, you get them from any fixed regular payoff function. There's always going to be a non-degenerate set of state variables such that this eta function is within the set or outside of the set. So we get a whole host of state variables under which the Nash equilibrium is learned with positive probability, and another one under which the Nash equilibrium is never learned, so that these algorithms are never going to learn to be competitive with each other. And if there are no questions, I can tell you that, once, for example, you have a situation where there is a state variable under which the static Nash equilibrium is never learned, then you could ask, okay, what are alternative equilibria that could be learned? Are there more equilibria of this game under that state variable? Will they be learned, or will some cycles be learned, or something like that? And the answer is that yes, potentially, there could be more equilibria, and they could potentially be the worst equilibrium in the regulatory sense. The most collusive equilibrium can be learned with positive probability if the Nash equilibrium that is the most competitive one is never going to be learned. Since I don't really have that much time, basically what I'm saying here is that there is a characterization of the most collusive equilibrium, at least if it is a symmetric equilibrium. And this characterization says that it's enough to look at binary state equilibria. So if we find some binary state variable that supports the best equilibrium, then it might support the best equilibrium. Yeah, so there is a binary state variable that will support the best equilibrium. And all I want to show you then is some quick pictures, which are the following. So I take basically numerical simulations of a nice regular payoff function game. First, I look at a state variable under which the static Nash equilibrium is always learned. So what this picture here shows is on the x-axis policy quantities in state A. So this is a binary state variable. On the y-axis, quantities chosen in state B. And this black dot here is the static Nash equilibrium. In every state, we play the same quantity, 0.3. And blue and orange dots are simulation outcomes for 2 reinforcement learners that learned policies over time, and under, I don't know, a couple million iterations, all of them from a global initialization ended up close to this static Nash equilibrium. So the competitive outcome has been learned with probability 1 in this case, under the state variable. Now, if we look at the same game, so it's the same market, the same agents, the same preferences, but a different state variable, here's the verification of the proposition I just showed you. Let's not look at that. Then, same initialization, here is the equilibrium that we just looked at, where players play the same action in every state. Then, from a global initialization, almost all of these simulation outcomes ended up here. And what is up here is the green star is a collusive equilibrium where in one state players play very low quantities, contracting supply, getting very high prices. And in the other state, they punish each other with some probability. And this is kind of an exemplification of how strong and how important these state variables are in learning. Even if you keep payoffs fixed, the choice of what information to follow when you're updating your algorithm is essential in what can be learned by these algorithms, and in, for example, whether collusion is learned or not. Okay, and I think this is where I should stop, and please ask any questions and confusion you might have. Thanks for listening.
Thank you, Clemens. Very nice talk, very clear. So maybe I start with the first question. So at the first part of your talk, you mentioned about this stochastic fictitious plane, right? And then for there, you take a random action with this parameter lambda, and it seems that this lambda does not affect the convergence of this ODE. Is it true?
In some so okay, so lambda you can think of, the larger lambda is, the closer you are to standard best response dynamics.
Right.
The equilibria I showed you here, they are equilibria of the ODE, perturbed best response dynamics, right? So these are equilibria of this guy.
Mm-hmm.
These are not actually Nash equilibria of the game where players choose true best responses, but these are Nash equilibria of the game where players have to choose these stochastic best responses. And that means for lambda that is not infinite, these are not going to be exact equilibria of the game. So what I'm saying is that, as you change lambda, the actual convergence outcomes of the process are going to change as well.
I see. So it's not
but
really.
The larger lambda is, the closer they're going to be to the Nash equilibria that the game has.
I see. So basically, this result is more like saying how the ODE predict this outcome of the algorithm, instead of how the algorithm learns the Nash equilibrium of the original game.
Yes, exactly. There are variations to this. You could, for example, introduce lambda as a function of n and increase it over time, for example. And if you choose the right speed for lambda, then you can actually show that the limiting ODE is going to be best response dynamics, and you're going to approximate those Nash equilibria. And you're going to learn this Nash equilibria instead.
Okay, very interesting. The second one is that you mentioned that in the second game, then this mixed strategy is not learned by this algorithm, right?
Yes. Yeah. So in reality, these are all mixed strategies because lambda is positive. As long as lambda is positive, any equilibrium here is a mixture.
Mm-hmm.
But the mixed equilibrium of the original game, correct? That's the one that is not learned. It's somewhere in here in the middle. And that's the one that's unstable under this dynamic.
So in this case, it means that is it saying that for this mixed strategy, is no algorithm can learn this mixed strategy, or it's just saying that learning this mixed strategy is not it's not practically interesting? I don't know.
Oh no, it might be practically very interesting, but an algorithm that is a stochastic approximation algorithm under which the associated ODE is unstable for this equilibrium will not learn it. There could be other algorithms for which the ODE is attracting at that equilibrium, and in which case it would be learned.
I see. Okay, thank you.
I have a question, but I remember you have your Carnot. I remember your Carnot game. You presented it, and you had this model where you have stochastic, choices of the players. We have a much simpler one, which is more like it's just a repeated Carnot game, a little bit along the where we haven't started it yet, but along the lines of the Calvano, Calzolari, etc. paper. So it's just a repeated game. You get the payoffs of the actual state game. Now, what I was thinking of, and this is my question, do I understand correctly? It didn't learn to collude in the Carnot game, or did it?
It learns to collude depending on the state variable that is used.
Okay, but yeah. So my thinking about this is, these concepts of, and that's something we were actually trying to investigate. The concept of strategic complements where there's substitutes. in the sense that if you, so that means the following, in the chrono game, if the other person produces more, your best response is to produce less. So these are what are called substitutes. Whereas, for instance, if you have a prize competition, which you can model with an approximate, I mean, Bertrand model, which is not as discontinuous as but sort of approximating a bit. It's the opposite. It means if you raise your price, the best response is also a higher price, although it would be lower than the opponent's price, and they will again converge to the Bertrand equilibrium. But I think there is a greater potential for collusion, even in a simpler game, not the one with the state variables, that has strategic complements. Because then, for instance, if you convert it to a leadership game, somebody goes first and the other person follows, there is an incentive for both to raise prices. Whereas in the chrono game, it's a fantastic fight because you want to be first all the time because you only lose out. And in fact, in the leadership game, so if somebody goes first, the other follows, both people follow. In fact, the follower more than the leader. So that was for me a reasoning to think not of chrono games, but of of prize competition games. And I wonder whether you have started to look into this idea that collusion is more supported by strategic complements than substitutes. It's an idea, and I think it's economically interesting. And we could follow up. I mean, this may be a bit special, but I think it's a concept that would nicely complement economic thinking in this regard.
Yeah, no. I think this is very interesting. I'm not sure. I wonder if I guess there's two things. So on the one side, thinking about the payoffs that can be achieved in a game with strategic complements versus strategic substitutes, and looking at the most competitive payoff versus the best, most collusive payoff. Maybe this distance increases under complements. That's basically talking about candidates. And the other thing, so that this would be totally unrelated in a sense to learning, but the other thing could be that it could be true that complements provide a stronger pull in the sense that the probability of learning those really bad equilibria is larger under complements than under substitutes. And yeah, I'm not sure about that one. That would be interesting. I'm not sure if the intuition.
Yeah, I mean, we could. I mean, I'm suggesting we could try. I mean, that's maybe. I mean, it's something that could be a nice research topic.
Yeah, absolutely.
And maybe something that is a little less dependent on this particular modeling of the state variables. I don't know. I mean, it's the repeated Nash equilibrium is the same. It's both goes back to the actual Nash equilibrium.
Yeah.
But, I mean, for instance, if you alternate, I mean, if somebody goes first, the other second, then it's a different game, and that's what I'm trying to say.
Yeah. Right.
Anyhow, it's just a remark, and it's specific to the chrono game.
Yeah. No, thanks, Bernard. Yeah.
Oh, and the second one, if I can say so, I mean, the general thing is, I mean, we have another prize competition game which you might know of. This is the Zelten demand potential thing that he got his Nobel Prize for. We invented subgame perfect equilibrium. And that is very competitive, but it's because it unravels in a sense, a little bit like, the centipede game where you should not cooperate because in the future, if you think too much in the future, it's all defect. It's a so I wonder whether equilibrium in the first place is the right concept, because a certain short-sightedness is probably what helps us, I mean, to cooperate, because we don't try to cheat on each other. I mean, and just because we don't know whether there's a tomorrow and so on. And that's a different aspect. So maybe it shouldn't be even equilibrium in the first place. Extremely exemplified, for example, in the Traveler's Dilemma, which is the simultaneous version of the centipede game, which you might know. So the question is equilibrium in the right concept here?
/ commitment.
Yeah.
Really, commitment is really important.
Yeah. Well, that's power too. I mean,
yeah.
Anyhow, this is just the things that go to our minds when we look at these games and try to study them.
Are there any more questions? Okay, then we thank you once again.
Thank you, everybody.